Now back to using Schrödinger's equation to find some wave functions for some sort of typical setups, typical situations, or in fact some of the simplest situations you can work with the Schrödinger equation to find wave functions, but that actually turn out to be very useful when you look at quantum mechanics in more detail anyway. So the first one of these wave functions we're going to look for the solution to Schrödinger's equation when we have this particular setup for the potential. So remember, in Schrödinger's equation, the only thing that really changes is that potential, right? It was u times psi. There was that term in there, and the other terms aren't really changing. So it's just that potential that's going to give us different wave functions out. This is one potential you could think of, known as the particle in a box, also called the infinite square well. That might be a better term because the potential is infinite outside of this region, 0 to L, and it's 0 inside. So this is our potential. Give it mathematically or functionally there, shown graphically here. There you go. That's the potential. And we want to see if we can find solutions to Schrödinger's equation for this particular arrangement of potential. In the regions where the potential is infinite, right, outside of this box, or outside of this square well, if the potential is infinite, the only way that you can really have Schrödinger's equation satisfied, or the simplest way to think about satisfying it in that area, is to have the wave function equal to 0. So 0 times the infinite, so just cancel out, the whole equation is 0, and it's just fine. So outside of the box, the wave function is 0. Inside the box is more interesting. We're going to figure that one out. And then one other thing to point out here is that these graphs can be somewhat confusing sometimes because we're talking about a wave function that is describing a one-dimensional particle. All the wave function is going to tell us is the probability of finding this particle somewhere within this box. But it's not even really a box, it's along a line, is a better way to say it, right? It's just along the x-axis, right? Probabilities to find it, say, in this part of the x-axis, or in the left side of this line, or on the other side of the line, right? Or in the middle-ish, right? That's what we're getting out. So even though this has that vertical axis for the potential, really the wave function exists kind of on the x-axis, or it's a one-dimensional function. All right, some bigger calculations here, bigger whiteboard. Let's do it again. So if you look back or think back, the first condition for our wave function is that it needs to be continuous, or this is that first condition. It's continuous. I'm not good at spelling too much. You get what I mean. But again, we said that psi just needs to be 0 outside of this box. So that means that whatever's happening in the middle, it needs to meet up at 0 and at L. This kind of picture here where so outside of 0 and L, the potential is infinite, so we said this psi has to be 0, meaning that for continuity to hold, whatever's happening inside has to meet up there. So psi at 0 needs to be equal to 0 to meet there, and that also needs to be psi at L, right, to meet up on that side. Okay. So if we write down Schrödinger's equation for inside of this box, well, I'll just write it as primes. So another way of writing this is, well, minus, I could, all of that. However you want to write it, the second derivative of the wave function is the opposite, and then some constant, of the original wave function, right? So you have something, y double prime is equal to like minus some constant value times y. And if you've done differential equations, or maybe you have not yet, but the things that satisfy this kind of differential equation are oscillating functions. So we're not going to go through the whole derivation, but essentially sine and cosine can be solutions to this, and you can just show that, prove that yourself. Just take two derivatives of sine, and you get back negative some constant times sine, or cosine. So in general, a solution to the Schrödinger equation inside this box, it's going to look like a cosine or a linear combination of cosine and sine. So in order to make this a particular solution for our situation, right, we have a couple of things to figure out. We need to know what is A, what is B, and what does K look like. Let's use our part of this continuity condition, because psi of 0 should be equal to 0. But if I put in 0 here, sine goes to 0, cosine goes to 1, meaning that A is all that's left, so A has to be equal to 0. So now we cut that term out of our wave function, and the other continuity condition looks like psi of L needing to be 0, right? But that's going to be B times the sine of K L. Well, one solution is that B is 0, but that's not actually a good solution because that means psi is just 0 everywhere, right? If B is 0, we already said that A was 0, so the wave function is 0 everywhere, which is not good because the wave function should give us probabilities, and if we integrate over all of the space, we need to get 100% probability. You're never going to get 100% when psi is 0 everywhere. So B can't be 0, which is telling us that this sine needs to be 0, and sine actually is 0 on repeating places. So where is sine equal to 0? Well, when its argument is some multiple of pi. And it could be 0, it could be 1, it could be 2, it could be 3. Get that. So what is this saying? That psi, function of x, looks like b times sine of, oh well, I want to replace k, so k is equal to n pi over L. N pi over L times x. So we still don't know what b is, and right now, n could be any integer, positive integer. However, if you look at this function, when n is 0, again, the wave function is going to be 0 everywhere. Regardless of what x is now, that n being 0 would cancel out the wave function everywhere. That is to say that we actually have to eliminate 0 as a possibility here. When n is 1, then we actually have a sine function. It's not just 0 everywhere, or for all x. Okay, so we can now find what b is given our normalization condition. So normalizing, again, is minus infinity to plus infinity. If you integrate over all x, you need to get 100% probability. And we've seen this integral, something very like this, a number of times. It's going to reduce down to this. Maybe the argument's slightly different, right? But it's a sine squared. I've seen that integral a couple of times. Yeah, I don't think we're going to go through it all. Turns out it's just L over 2. That's what this guy ends up getting. So what does that mean? That means that b multiplied by 2 divided by L square root actually looks very similar to what we found before too, because we had a wave function very much like this before already. Okay, so this then is our wave function that has now been normalized. So it's going to get proper probabilities. And remember, n couldn't be 0, but it could be 1, 2, 3, it could be all those things. And since it's now indexed by n, we will generally write a little sub n there to indicate that there's different wave functions depending on that n value that you choose. So if you look back here, this was a general solution to this differential equation, this version of the Schrödinger equation. The last thing that's still kind of floating around and unknown in here is E, is the energy involved. What is that? Well, I need more room. Now that I have the particular, the full sort of solution here for the wave function, I can now just put it back into Schrödinger's equation for our particle in a box, and I should be able to get out what the energy of these different wave function states are that are indexed by n. So it's going to involve taking two derivatives of this wave function. Pretty straightforward though. One derivative is going to give me cosine with this extra stuff inside of the argument, right? Not x, because x goes away in the chain rule here. And then the second derivative is going to give me another factor of this n pi over L, and the cosine is going to go back to the sine. We're going to get a negative sign overall. So that is all to say, we're going to get negative n squared pi squared over L squared, right? One factor from each derivative. And we're back to sine. So that's the second derivative of our wave function. It should be equal to these energies that we're looking for, multiplied by the wave function, or yeah, I'll just leave it as the wave function. Because if I look at this, this part plus this, right, that's just the wave function. That's the original psi. Root 2 over L times the sine of n pi over L times x. There's two minus signs here, so we're end up getting a positive overall. I'm going to write this guy still separately here. L. But this is really what we have. Put all that stuff back together to get psi, which is not a coincidence that the second derivative of psi gave me back psi with some stuff and a negative sign. That was by design. That's how we picked our wave function, is that it satisfied this. And since psi is not 0, just divide by psi. And finally, we actually know what our energy is now. Replace h bar over 2 with just h, Planck's constant, over 2 pi. Then the pi's are going to cancel. You can probably do this. End up with h squared over 8 times the mass times the length of this box squared. All of that multiplied by this n squared factor. And again, just like the wave function, this energy is indexed by n. So we can write a little sub n, indicate that, and also indicate, remember n can be 1, 2, 3, 4, it couldn't be 0 though, right? 1, 2, 3, 4, 5, all of that. There you go. And there we have it. Right? We have our wave function, our time-independent wave function. Right? We're not dealing with time right now. And it looks like this sine function, and it actually is, there are multiple wave functions actually here, depending on the n value, that integer n. And we also have the energy of these wave functions, or these states, which is also indexed by n. The book keeps h bar and the pi's around. I don't know, I think it's a lot cleaner if you replace h bar with h over 2 pi and get rid of those. So that was the one I got in the derivation over there. But yeah, it's basically some constant stuff, well, for a particular particle, h m, and a particular length of this box L. It's just those values multiplied by this integer n squared. So it turns out that this n, even though it kind of just came out of the fact that sine is oscillating and has these multiple zeros, n is a very important thing. It's what indexes the wave function, the energy levels. This n in particular is known as the energy quantum number, or also known as the principal quantum number. And let's just think about it. So what's the lowest energy state that we could get for this scenario, this wave function? It's when n is equal to 1, right? Remember, n can't be 0. So the energy just looks like all those constant values. The wave function, well, pretty straightforward. The n is just 1, looks like that. Pretty important though that the lowest energy state possible is not zero, right? You can't have energy equal to zero in this scenario with this particle in a box or this infinite square wall. There is some lowest amount of energy that's non-zero. That means that the lowest energy state is not equal to zero. It's some amount of energy. And it's just interesting to point out that that consequence really came out of the fact that we were interpreting the wave function for the square of the wave function as giving us probabilities. And when n was zero, the wave function would have been zero everywhere, which gives just nonsensical probability. If you're saying the probability of finding something everywhere is zero, then there's nothing there. What are you talking about? So this fact that there is no zero energy level is quite interesting, and from even more so when you think about it, just from the fact that we're thinking about psi as giving us probabilities. What does it look like then if we visualize a few of these wave functions and kind of correlate them with these energy levels? So on the left side, drawing out some of these wave functions, say when n is equal to 1, to 2, to 3, that's what the wave function looks like. We're left b in there to just make it look a little bit simpler. But essentially all it's doing is going from half wavelength, where psi is this half wavelength in this box, to adding on half wavelengths, right? Go half wavelength to a full wavelength, to 3 half wavelengths, the next one 4 half wavelengths, or 2 wavelengths. So that's what's happening to psi, to the wave function, as we increase that quantum number, that principal quantum number n. The vertical axis on the left there really doesn't mean anything. They're just kind of spread out in order to line up with the energy levels on the other side. On this graph on the right here, we actually have energy being plotted where the vertical axis is the energy. And so for the ground state, for the lowest energy state, when n is equal to 1, we get all those constants, h squared over 8 times n times l squared. That's the lowest energy state. And then they just increase in this way because n is increasing 1 to 2 to 3 to 4 to 5 to 6. And the energy of these states is multiplied by n squared. So the ground state has this factor of 1, 1 squared is 1. The next energy level, or the first excited state of this particle in a box, is all that stuff multiplied by 2 squared, by 4. Second excited state, or n equal to 3, is multiplied by 3 squared, or 9. And it just keeps going up in that way. As you can tell, the energy levels are spreading out more and more and more because you're going by n squared. So thinking a little bit more about these energy levels then, it's very much in line with what we saw in the last chapter, where energy in the quantum world, or in quantum mechanics, is quantized. That is to say that it's discrete. There's only certain amounts of energy that something can have. So in the case of this particle in a box, it can only have this lowest energy level. It's the lowest it can go. Or it can have this next one up, right? It can't be anywhere in between there. There's not a continuous spectrum of energy for this particle to have anymore. It has these discrete values. Which also means that it can only gain or lose certain quantities of energy too. If it's in the ground state, then it needs to gain 3 times that h squared over 8ml squared, 3 times that amount in order to get up to the next state, ground state to the first excited state. Or it could gain 8 times that amount and get up to the second excited state. So since it's not this continuous spectrum of energy, then the only way it makes sense for them to go from one state to the other is instantaneously. There's essentially just no energy space in between there. There's nothing there for them to like move from one to the other. So that means they just have to instantly jump from one to the other. Say a particle in this lowest state gets 3 times all those constants and it instantly jumps up to the first excited state. Or say a particle in the second excited state, n is equal to 3, loses, say, 5 times all those constants and instantly jumps down to the first excited state. There's no place in between there for the particle to be, so it has to just jump immediately down to there. Alright, let's do an example that uses some of this new information about particles in boxes. And again, remember, it's one-dimensional, so it's really more like a particle kind of on a line. It's confined on a line. But suppose a proton is confined to a box of width 10 to the minus 14th meters, and it's in fact a typical range for the radius of a nucleus. What are the energies of the ground state and the first excited states for this proton. And then if a proton makes its transition from the first excited state to the ground state, what are the energy and the frequency of the emitted photon? So when we're talking about these particles in boxes, the way that they're absorbing or emitting energy, one way to do that at least is to absorb or emit a photon, at least if they're electrically charged particles, like a proton. Well, that energy level requires the mass of this particle. The mass of a proton is this 1.76 times 10 to the minus 27 kilograms. It's about 2,000 times larger than the mass of an electron. So what does the ground state energy look like? Remember, n equals 0 doesn't exist, so the ground state is n equals 1. So that's what we would get for our first energy level, or our ground state energy. So that h is going to get squared. That, and then I'm just going to write that length is 10 to the minus 14th meters. Oh, and that's also squared. Ooh, that's getting tight. Well, hopefully, see what I'm saying there, even if it's a little bit hard to read. But when you plug all those numbers into a calculator, you're going to get 3.28 times 10 to the minus 13th. And we can convert that to, say, electron volts. 2.05 times 10 to the 6th electron volts. Or we could use mega electron volts, 10 to the 6th electron volts. So 2.05 mega electron volts. So this is the energy of the proton, this proton that's confined into a box, which is essentially the nucleus of an atom. What about the first excited state? So n equals 1 was the ground state, n equals 2 is the first excited state. Well, I could re-put all those numbers in again, or I could go back to the fact that the excited states are just the ground state multiplied by the quantum number squared. So that looks like 8.2 mega electron volts. There you go. If this proton then makes a transition from the first excited state to the ground state, what are the energy and frequencies of the emitted photon? Well, the only energy it can be, right, because this energy is discrete, it needs to be the difference in energy of the first excited state and the ground state. That's the energy that the proton loses when it drops down. That's the energy that has to leave. So we can find that pretty simply, just take the difference of them. And that turns out to be 6.15 mega electron volts. If we want to know what that frequency is, we can go back to our quantized energy for a photon. So that the frequency is that energy divided by h bar. Frequency then looks like 6.15 mega electron volts divided by, and this is actually going to be h, Planck's constant, in units of mega electron volts times seconds. 4.14 times 10 to the minus 21st. So we end up with 1.49 times 10 to the 21st hertz, right? Units of mega electron volts go away. 1 over seconds is hertz. If you look up in an electromagnetic spectrum, this range is what we call gamma rays. And as the book points out, these frequencies, these photons, are something like 10 million times greater energy than visible light, or visible photons. Quite a lot more energetic. So when you talk about smaller and smaller spaces, tend to deal with much larger energies. Something we generally want to check is we get a wave function, we get a solution to Schrödinger's equation. We want to make sure it still makes sense if we imagine going back towards the classical sort of setup. That's again our correspondence principle, so kind of checking if correspondence makes sense. Or a correspondence check, if you will. So this is our wave function, or technically the probability is the square of the magnitude of that wave function, so that's the square of the magnitude of the wave function. If you plot n equals 1, right, the ground state wave function here, then you get this peak, right, which tells me that my particle tends to be more likely found in the middle of the box. But if you think about just like if there's a ball, say, in a box or in a tube, back like we were thinking earlier on, like in a classical sense, there's no real reason for that ball to be anywhere in particular in that tube, meaning as it should be pretty much an even probability of being found anywhere in that tube. However, our quantum particle in a box is preferentially found in the middle, at least when n is equal to 1. When n is equal to 2, the first excited state of this particle in a box, it switches up. The probability of finding it actually in the middle is now 0. You don't find the particle in the middle at all. It actually is preferentially found in these two areas, sort of at the quarter ways along this box. You get these two different peaks. However, if you look at larger and larger n values, or higher and higher quantum numbers, principal quantum numbers, that's where we get back to a more classical realm. When you're talking about larger and larger quantum numbers, you're talking about larger and larger energies. And one region where we get back to sort of a classical picture is with larger and larger energies. So larger and larger quantum numbers should get us there. Here we're just showing n is equal to 20 state, or the 19th excited state in this for this particle in a box. And you see it's just this like oscillating thing. It has a pretty sort of short wavelength relative to the width of this box. And you can imagine larger and larger and larger and larger numbers, like you talk about like n is equal to 100, then you're almost not even going to see the oscillations of this wave function anymore on this plot, right? It's just going to look like a line, which is good because that's telling you that for large quantum numbers, the probability of finding the particles somewhere in the box is pretty much even throughout that whole box, just like you would expect for a classical situation. So correspondence checks. So that was our particle in the box. Another sort of standard situation to look at when you're initially getting into quantum mechanics happens to be a harmonic oscillator, like a spring potential energy. In classical physics, you tend to look at this simple harmonic oscillator quite closely, and for good reason. The reason being that in quantum mechanics, pretty much everything turns out to act like oscillators. So the way that a harmonic oscillator acts is actually very broadly applicable. But first, let's just think about this classical harmonic oscillator. Simple harmonic oscillator is just like a mass on a spring oscillating back and forth. We're assuming there's no friction, there's no heat being generated by the spring, so essentially this mass is just going back and forth and it's going to continue doing the same motion over and over and over again forever. The potential, that spring potential energy here looks like 1/2 the spring constant K, right? K is the spring constant now, not the wave number, multiplied by the position of that mass squared. And the position is measured from the equilibrium. And then the total energy, you'd say, of this oscillator is just that spring constant multiplied by the full amplitude, or the amplitude of this oscillation squared, divided by 2. And what's happening, if you remember back, is essentially an exchange between kinetic and potential energy that's continually happening here. Right at the equilibrium, right at 0, the potential energy is 0, and all of this oscillator's energy is kinetic energy. So it's moving fastest right at that center. Versus at the end, at the edges, at plus and minus A, these are the turning points, and these are classically the limits of this oscillation. This object is not going to go further than that because it runs out of kinetic energy and converts it all to spring potential energy, and then it gets reversed and starts going back the other way. So at the ends, it has no kinetic energy. It's moving its slowest sort of in the edge regions, which is also to say that if you were to ask, where am I most likely to find this oscillator? Well, it's out at the ends because it's moving the slowest there. So it spends the most time out on the sides, meaning you're most likely to find it there if you're just randomly checking to see where it is. Versus in the middle, right, it has the largest kinetic energy. It's all kinetic energy there. So it's moving very fast. It doesn't spend very much time there. So if you just randomly check on it, it's not very likely you're going to find it there. And one other thing to point out then too is classically our harmonic oscillator can have zero energy. There's no problem with that. All that means is that the oscillator is not moving. It's at its equilibrium point, zero potential, zero kinetic, total energy is zero. Totally fine. Now we want to transition to a quantum harmonic oscillator. And to do that, well, there's a couple of things you could think of, but basically we want to stop talking about a spring. There's no spring involved anymore, but there is a potential that has this. It's this quadratic potential. So to get rid of that k, that spring constant, we can rewrite this potential in terms of omega, the angular frequency, instead of k. To do that, this is the form of our potential for our quantum harmonic oscillator. It's a quadratic potential. If you then put that potential into Schrödinger's equation, this is what you'd get. Now we do have a potential term. It's not zero. It looks like that, and so it multiplies psi. So this is a second order linear differential equation. I'm actually even sure off the top of my head. Solving it right now is beyond this course. We don't need to solve it. So I'm just going to give you the solution. We're going to talk a little bit about it. There you go. If you were to solve that differential equation, Schrödinger's equation, for the quantum harmonic oscillator, you get this as the energy states. Remember, we're still talking time independent, so these are what you would call stationary states or stable energies, stationary energies. This is what you get for the energy states, again indexed by principal quantum number n. This is what we would get for the wave functions, also indexed by n. It's fairly complicated. Beta is a substitute for that square root of m omega over h bar. Capital N sub n is a normalization constant that actually also depends on the principal quantum number. We're not even really going to touch on what that actually is, or the form of that. But we also then have this capital H sub n. Those turn out to be what you call the Hermite polynomials. And these are the first four Hermite polynomials. So for h0 of this y, instead of beta x, just replace y with beta x and get that function, that form there. But if we're just saying the Hermite polynomial is for h of y, the 0, 1 is just 1, pretty simple. The n equals 1 is 2y, this is a linear function. N equals 2, 4y squared minus 2, it's a quadratic function. N equals 3, it's a cubic function. And also notice we're going even to odd functions too. Even, odd, even, odd. So again, the actual mathematics here is fairly complicated. We don't really need to get into all that, but we can at least take a look at what these wave functions look like. This was my attempt at showing you how we get from those pieces that make up the wave function to the full wave function. Mostly what's making up the form of this wave function in the end is a combination of that exponential that was e to the minus x squared and these Hermite polynomials. Remember, the first Hermite polynomial was just 1. So when n is equal to 0, the wave function just acts like e to the minus x squared. And that function is like a bump. Something along the lines of a Gaussian function, what you call a Gaussian. But it's basically just this bump around 0. When we go to n equals 1, there's more stuff that happens, but the very simple picture is that we now have still that exponential, e to the minus x squared, but the Hermite polynomial is this odd function now. So we still have that red exponential, but now we're multiplying it by this polynomial. So when you multiply the red and the blue together, or you combine them together, we end up getting this black result, which is actually down on the left side and back up the other side. N is equal to 2. Again, that e to the minus x squared is always there. It's just the Hermite polynomials are changing. N is equal to 2. We have this x squared, and it's offset actually if you look at the back of the Hermite polynomials. But basically, it's this e to the minus x squared multiplied by this even function. So the result of combining that parabola with the e to the minus x squared, or that offset parabola, that's the black. That's what we end up getting there. N is equal to 3. It's getting a little more complicated, but you can see if you combine the exponential and the Hermite polynomial, black's the result there. So here again we have another graph of these wave functions. Now they're kind of overlapping on this energy scale. Remember again, the wave function is not in units of energy, so the up and down of the wave function here doesn't really have much to do with the energy, right? Because the wave function squared is our probability. The places that they're at, those horizontal dotted lines, that's the energy of each of the states. Essentially, you have the energy of like the ground state, and drawn over it is the wave function for the ground state, or the energy level of the first excited state. Drawn over that is the wave function for the first excited state, and then keep going up. Also note that this graph is drawn in units of h bar omega, and if you look back at the energy is basically just, well, the energy was n plus 1/2 times h bar omega. So it makes it a little bit cleaner to graph it in units of h bar omega. So you're basically just taking that part out, and what we got up here is just 1/2, 3/2, 5/2, etc., etc., etc. Now, some things to point out that are different than the classical harmonic oscillator. So just looking at that first state, that ground state, n is equal to 0. That wave function peaks actually in the center of this potential. And if you recall back, the most likely place of finding the classical harmonic oscillator was at the ends of its oscillation. This is the opposite for our quantum harmonic oscillator. It's actually most likely to be found, at least the ground state, most likely to be found in the center, or around that equilibrium. Also, remember that those horizontal dotted lines are the energy of these states. And classically speaking, once that energy sort of meets up with the potential, that's as far as a classical oscillator will go, right? That's when all of the oscillator's kinetic energy has converted to potential, and it is stopped, and then it goes back in the other direction. That is to say that the probability of finding a classical oscillator outside of those regions where the total energy meets up with that potential energy is 0. You can never find it outside there. That amplitude of the oscillation is the limits of where you can find that oscillator. It's not the case here, right? Shown on, say, the ground state, where the ground state level energy meets up with the potential, well, the wave function just keeps going outside of that, right? So it's petering out, but it's still non-zero outside of there, meaning that there is actually some chance, some probability of finding the particle outside of this normal region, or outside of the classical region. Give a quick little correspondence check, right? We want to make sure that when we get to classical regions, we still get classical results. Again, when you go to larger and larger quantum numbers, larger and larger energies, you're getting back towards classical regions. So if we look at, say, even the 12th state, right, n is equal to 12 for our wave function, and this is showing the square, the magnitude squared of the 12th energy state, then this is the picture we get. This is the probability, or the probability density. And what it's looking like is that that probability density is starting to peak now towards the outside again, which is good, right? If we go back towards the classical region, we should get our probability of finding that quantum oscillator is greatest at the outside, or at the edges of the oscillation. And then also you can notice that the bit that's actually outside of the classical limit, right? The classical limit is just plus to minus a. There's still some of this wave function that exists outside of that limit, but it's pretty small. And in fact, as n keeps going higher and higher and higher, then these peaks are going to get closer and closer and closer together, so you almost get this smooth curve, and the amount of the wave function that's outside the classical limits goes to 0. So there you go, we get back to our classical picture. The idea then that a wave function, or in some sense a quantum object, has a probability of being found in these like forbidden regions that, at least as far as classical physics was concerned, leads to a very interesting result when you consider what happens if you have a barrier. So like a potential that peaks, or that like jumps up somewhere, but is 0 elsewhere. When you have that sort of potential, again, the mathematics is beyond this course, we're not going to worry about that. I don't know why the book spends so much time on it. We're just going to get the sort of short version summary, which is that you have this potential, right? There's essentially kind of this wall, and you think about what would the solution maybe be like, or the wave function be like, if the energy of a certain state is lower than the height of that wall. So the potential is 0 everywhere except for some constant value, right? That's our wall. The process of doing it is you have to break it up into these 3 regions. Then you think about in these outside regions, it's sort of like a free space region, so we actually end up getting plane wave, and you think about then the situation as like a plane wave approaching this barrier, this incident plane wave, and some of that wave gets reflected, and maybe some is able to be transmitted. So the result of all this stuff with Schrödinger's equation basically is that you get a portion, or how much of this wave is reflected and how much it might be transmitted. And you see just from the graph of the solution to Schrödinger's equation for this setup, you get this plane wave, and then in the region of the potential of that barrier, you end up getting this decaying exponential. And then again on the other side, as long as that exponential hasn't decayed to zero, then you can get some part that's transmitted. Much smaller amplitude, but some of it's still there. This process is usually referred to as quantum tunneling, and it's a tricky thing maybe to conceptualize at first why it's so strange. But the fact that you have like these waves coming into one side of this barrier, and the energy of those waves is less than the height of the barrier, even still, there's some probability that some of the waves will go through. It's a very strange thing. Actually, I think I have an animation for it in a second. Oh yes, very good. So the derivation of this quantum tunneling, you need to think about waves. However, there's a very useful analogy here where instead of thinking about a wave, you can think about like a ball that you're trying to roll up a hill. When you take a ball and you roll it at a hill, right, you're giving it some amount of kinetic energy. And assuming, it's not losing energy to friction or anything like that, then that kinetic energy is determining how high up the hill it gets. Right? Because as it goes up the hill, it's exchanging that kinetic energy for gravitational potential energy, and it only has so much kinetic energy that it gets so high, and if the hill's higher than that, it stops and it comes back down. So on the left you have this classical picture, right? The energy of the ball, the kinetic energy that you gave the ball, is less than the potential of the hill, or the gravitational potential associated with the height of the hill. In classical physics, that situation always ends up with the ball not going over the hill. Think about it, you roll a ball with not enough speed to get over a big hill, it's just going to roll up and it's going to come back down. Every single time. No chance it's going to be on the other side. What quantum mechanics is telling us in this quantum tunneling thing is that even if you have a particle that's incoming on this barrier, like you're rolling a ball, but its energy is less than the height of that barrier, there's still a possibility that it can make it through and be found on the other side. So in this quantum ball rolling picture, you have a ball that doesn't have enough kinetic energy to make it all the way up, except that there is some chance that it gets up to some height and then instantaneously just pops out on the other side and rolls along. Wild stuff. Wild stuff. So yeah, the only real quantitative thing to get out of that quantum tunneling for us, or for us in general, it's too much. But we can at least look at what's called the transmission coefficient. So right, I said in the end you essentially get some amount of this incident wave is reflected and some is transmitted. So there's a reflection coefficient, there's also this transmission coefficient. It is proportional to, or it goes as, this e to the minus 2 times g times L. L is the width of that barrier. That is to say that transmission coefficient, or essentially the probability that you'll find the particle on the other side of the barrier, is correlated very strongly with L, with the width of the barrier. Which makes sense if you think back as, inside that barrier, it's just this decaying exponential. So if the barrier is pretty long, then it's going to decay to 0 before it gets to the other side. Very little chance that you'll get transmission. G is actually all of this stuff, square root 2m multiplied by the height of the barrier minus the energy of the incident particle, or the incident wave. All that over h bar squared. So G really just depends on the difference between the height of the barrier and the energy of that incident wave, or the incident particle. So that transmission also depends on that difference, but it's the difference and then it's the square root. So there's less of a dependence on that than there is just straight on the width of the barrier, on L, or the length of the barrier. So there are practical applications for quantum tunneling. We'll talk about, I think, one or two of those in a second before we end. But beyond applications, or just purely applications, quantum tunneling plays an essential part in existence in general, because the process of nuclear decay is actually a quantum tunneling process. if we look at the picture of the potential associated with a nucleus, R is like the radius of the nucleus. So inside of R, the potential is negative, and it's very low, right, or a very large negative amount. And then right at the edge of the radius, we sort of have this transition where the potential jumps up and then falls off. It actually falls off as 1 over R. Because in fact, the potential out here is actually due to the Coulomb potential. So this is like the potential between a plus and a minus charge. That's the potential you would draw for that. So if you have a particle, like an alpha particle, that's inside of a nucleus, well, an alpha particle is kind of a cluster of 2 protons and 2 neutrons. But if you have one of those inside of a nucleus, then you can understand some nuclear decay as that alpha particle tunneling, quantum tunneling through this barrier, sometimes called the Coulomb barrier. Those particles don't necessarily need to have enough energy to go over the barrier, because even if they're below that, there is some probability that they can be found outside of that barrier still. And once they're out, the potential just pushes them away. So remember, the length of the barrier made a big difference in how likely quantum tunneling would happen, how likely you would find that particle on the other side of the barrier. In this case, since the other side of the barrier is not a straight up and down line, it's this curve, the length of the barrier actually depends on the energy state of the alpha particle, or the particle that's trying to get out of the nucleus. So a higher energy level sees a shorter length to go across, which sort of makes sense. Higher energy stuff bouncing around inside the nucleus, more likely that it's going to be able to get out. So this quantum tunneling, or the likelihood that you'll get an alpha particle outside of this barrier, is directly related to decay properties like lifetime and half-life. Alright, almost done here. One very cool application, very powerful application of quantum tunneling has to do with what's known as a scanning tunneling electron microscope. And again, details probably too much for this course, but basically you have this tip for this microscope now, and it's kind of just like hovering really, really, really close to the surface of something that you're trying to get a picture of what that surface looks like. The tip is like a couple atoms across. It's an incredibly small thing to look at. And you have the tip very, very close, and essentially you have a small voltage between the tip and the material that you're trying to scan. And that distance between the tip and the surface ends up acting like the barrier in quantum tunneling. So the fact that the length of that barrier affects very strongly the probability of tunneling means that the distance between the tip and the surface is pretty easily to tell, because you get a much stronger current, or you get a large increase in current when the surface is just slightly closer to the tip, or you get a much lower current if the position on the surface is further away from the tip. You have this incredibly fine resolution depending on where this tip is. As you move it along a surface and the surface comes up and goes down, you get a change in the current due to this tunneling of electrons across that sort of vacuum between the tip and the material. Pretty incredible stuff. The resolutions you can get with this is laterally a 1/10 of a nanometer, and vertically, the vertical height, like down to 1/100th of a nanometer, 1,000th of a nanometer, 10 to the minus 12 meters. Really tiny stuff. And this is the kind of picture you can get. This is actually a carbon nanotube. And those spots, those dark spots, are carbon atoms. Or maybe not individual atoms, because I think carbon nanotubes are made up of like hexagonal. I'm actually not sure. It's either individual carbon atoms or 6 carbon atoms together. But either way, that's crazy. They're getting atomic scale resolution here. And it even has this kind of helix twist going on to it. Yeah, and they point out too that the colors aren't there. Like, all you're getting is information on how far away the surface is from the tip, so you can colorize these things to make them a little more appealing and, like I say, bring out some of the details. And this is where we're going to end. Like I said, didn't worry too much about time-dependent wave functions, and when we did, we just said it was at a particular time and t was equal to 0. Dealing with time-dependent functions means these are, I forget the term. Well, they're partial differential equations dealing with second derivative of x, first derivative of t. It gets rather complicated rather quickly. But just to show you, this is the time-dependent Schrödinger equation, and also if it's free space, so there's no potential, that's what the free space equation looks like. And not only the wave function can depend on time, the potential can depend on time as well. It doesn't have to, but it can. And just like we did with the kinetic energy and the momentum, we ended up kind of reassessing what those meant in the quantum world, and instead of being just quantities themselves, they now become operators, where those operators along with the wave function can give us probability of finding certain amounts of momentum or kinetic energy or position. So in that case, if you look at the time-dependent Schrödinger equation, there's something else now. It's not E, there's not stationary states anymore. That E gets replaced by the energy operator, which ends up being I h bar in this first derivative of time. And the last thing maybe to say about this is that this is a non-relativistic wave equation. If you were to continue deeper into physics, you eventually get to a relativistic wave equation, which is known as the Dirac equation. And funnily enough, if I remember correctly, it comes partly from doing that similar thing that I showed you at some point a while ago, where you kind of multiply by 1 in a really weird way, actually having to do with matrices or identity matrix. And by doing that and then splitting that one in a certain way, you can end up making a version of this that's, well, you incorporate relativity, but it also ends up being kind of symmetric in time and space. Not that you need to know any of that, I just thought I'd mention it anyway. And this time I actually look forward to the next chapter already, so we can look forward to more stuff with the Schrödinger equation, but particularly having to do with applying the Schrödinger equation to like an atom, meaning we're talking about the potential, or the Coulomb potential, between like a proton and an electron, or multiple protons and multiple electrons. And in doing so, we're going to end up seeing how the atomic structure that we know today, how we get that out of quantum mechanics, and a very fundamental explanation of why the periodic table is the way it is. Good stuff. All right, so see you then.